Thank you. This report is based on a joint work with Lev Idels from the Vancouver Island University in Canada and Ramazan Kadiev from the Dagestan State University in Russia. So this is the outline of the talk. I start with the deterministic McKendrick-von Foerster equation, which I will abbreviate to MFE. And this is kind of a conservation law in population dynamics. Then I will show how one can derive age-structured models from this conservation law using one particular example, Nicholson's blowflies equation. This part will be purely deterministic, but then I show how one usually appends a stochastic noise to an age-structured model. This is usually done in an additive way. However, this assumption, additive stochastic noise, doesn't seem to be well justified usually, as I will try to show today. So I will demonstrate that adding a stochastic noise, so stochastic noise should be added twice, once as an additive noise and also as a multiplicative noise. To show this, I go back to the conservation law MFE, McKendrick-von Foerster equation, add there a stochastic noise, and try to deduce a stochastic version of Nicholson's equation from there. So from the first principles, as one says in physics. And then I look at what I get, and this will be quite different from the model with an additive stochastic noise. And this will be in the last part of my talk. So this is the plan. So let us look at the McKendrick-von Foerster equation, MFE. U is the density of a certain population of a given age A and a time t, and M will be the per capita mortality rate. To deduce the conservation law, we'll let time to be t plus h, so that the age of the population will be also increased by h, so that a becomes a plus h, and then we can calculate the rate at which the population is changing in time. Then we get this expression, and in the limit we get the sum of the two partial derivatives. On the other hand, this rate must be equal to the number of individuals of age A who die at time t, which can be calculated using this product. So this is the mortality rate, and this is the size of the population. So this rate must be equal to the number of individuals who die at time t. And this is the McKendrick-von Foerster equation. In addition, we have to add initial and boundary conditions. The initial condition for MFE is standard, and it is defined using the function chi of A, which is the initial age distribution. And to derive the boundary condition, which is also known as the renewal equation, we have to introduce the per capita birth rate beta of TA, so that this product under the integral beta times u is the size of the newborns from the adults of age A, so that the total size of newborns will be this integral from 0 to infinity, and this size, the total number of newborns, is exactly the value of the function u of t0, at h0. So this gives a non-local boundary condition for the McKendrick-von Foerster equation. Now I want to demonstrate how to produce the age structure model from this conservation law. In this case, it will be, as I said, Nicholson's blowflies model. So this is the well-known Nicholson's blowflies model, where A is the density of the adults of the population. At time t, delta is usually stands for the per capita adult mortality rate, and capital P, theta, and tau are some non-negative constants, usually positive constants. So tau is the maturation period. P and theta depends on the population. So this model can be, and its generalizations, of course, can be derived directly from the conservation law, from MFE, in the following way. First of all, we have to introduce two another variables, so-called aggregated state variables. One for the juveniles, where we integrate the size of the population from 0 to the maturation time, tau. And another variable will be A of t, which is the size of the adult population. So these integrals, the second one at least, it's not necessarily well defined, but it can be proved under some assumptions that this integral converges, must converge, of course, because this is the size of the population, but mathematically it can be proved as well. In particularly, if we assume that the mortality rate M and the birth rate beta are different for these two groups of populations. In what follows, I assume that the mortality rate of the juveniles is a function of the size A, so the size of the adult population. It can be generalized, but if you want to deduce Nicholson's blowflies model, then we have to assume this. And similarly, the mortality rate for the adult population is also a function of the size of the adult population. And a similar assumption applies to the birth rate, where 0, of course, is the birth rate for the juveniles, and B is the birth rate for the adults. And this is again a function of A, and all these functions are Lipschitz functions. So this second assumption simplifies the non-local boundary condition, because if we integrate from 0 to infinity, then the part from 0 to tau will be 0, so that we are left with integral from tau to infinity, and beta is independent of A by our assumption, so that it can be set outside the integration. So we end up with B times the integral of tau to infinity of u, which is A. So this is the simplified version of the boundary condition. To derive equations for the aggregated state variables, we have to integrate MFE. Okay, if we want to derive an equation for the variable A, the size of the adult population, then we integrate from tau to infinity, so that we get this simple formula. The left-hand side will be then equal to A prime, the derivative of A. Mj is again independent of A, so we are left with the variable A on the right-hand side. So we only have to calculate this term, and it can be shown that at infinity this is equal to 0, which is also a natural assumption, because again this is size of population at the age equal to infinity. So this can be verified mathematically. So we are only left with this term u of t and tau, and this term can be calculated using integration of this partial differential equation along the characteristics. So this simple task, we get this formula based on the exponential integral of m, and this can be simplified to this product, because u at 0 is a product of b and capital A. Summarizing, we get this expression for the variable A, this equation for the variable A. And if we additionally assume that the birth rate function for the adults is an exponential decayed function with these two constants, P0 and theta, and in addition assume that the mortality rates are constants, positive constants, then we end up with Nicholson's blowflies equation. So this is the equation, Nicholson's model. Delta replaces MA, which is constant, the mortality rate for the adults, and this part is a nonlinear delay-dependent production part, as it is called. So this production part, this is the degradation part. But we have to remember that P, this capital P constant, which you have in the Nicholson model, depends on P0, and in addition depends on this exponential, which is also constant, but still this has some consequences for the stochastic model. We can also deduce an equation for the juveniles if we integrate MFE from 0 to tau and use similar tricks. Then we end up with this equation here. I don't use this equation today, but it can be done. So this is the second equation, which is usually which is contained in the system for the variables J and A. But in the case of Nicholson's model, we only have equation for A, and this equation is at least at the level of the variables independent of J of T. So how to incorporate stochasticity or uncertainty into a deterministic model? A usual way is to append an additive noise term, which in most cases is a weighted white noise. G is diffusion, B dot is the formal derivative of the Brownian motion form, because this derivative doesn't exist. B is nowhere differentiable, and J may depend on the solution A of T. So that usual way to incorporate stochastic noise is this equation here, where the deterministic part is the same as before, and in addition we have this stochastic noise. And usually this is interpreted as uncertainty, so this term is interpreted as uncertainty in the mortality rate. So these two parts are somehow connected. This equation is formal because this derivative doesn't exist, so I have to use integrals or this differential form, standard form for any stochastic equation. So this is the same equation as this here. However, if we go back to the biological meaning of the parameters of deterministic Nicholson's equation, then we have to remember that P, this constant, it is constant, but this constant depends on the mortality rate mg of the juveniles. In the deterministic case, this is still this term can be interpreted as the production term because, okay, just up to this rescaling. So P is the production coefficient, production term up to the scaling. But in the stochastic case, mj may be a stochastic process, so it is not that simple. You cannot simply rescale P and say this is the production coefficient, because it depends on the mortality rate. And this observation has, as I said, consequences in the stochastic case. So now I will demonstrate how to calculate this additional stochastic noise using the first principles, the conservation law, the McKendrick-von Foerster equation. To do this, I introduce a stochastically perturbed mortality rate, which is usually done at the level of the model itself, but not at the level of the conservation law. Now the mortality rate is uncertain, and this is the noise, nu dot, and I assume that this noise can be represented using the standard white noise B. So this integral, stochastic integral of some function g, and g depends on A as well, on the size of the adult population. So that the stochastic version of MFE will contain this additional term, this additional noise, or expressed in terms of the white noise, it will be this nonlinear term, which of course should be interpreted as an integral equation. So we have to rewrite this in the integral form, which yields this integral equation, where we have the Lebesgue integral here, and the second will be then the eta integral, the stochastic integral with respect to the Brownian motion. From this integral equation, we directly obtain this equality, where we replace 0 by tau, the maturation period. It is just an algebra, so we subtract the integral from 0 to tau from the integral from 0 to a, then we get this quality. And now we can let a go to infinity, so that from this we get an equation, an integral equation for the size a of t. So this term, if a goes to infinity, will give us a of t, the size of the adult population, total size of the adult population at time t. The second term will produce the size of the adult population at time 0. Now this part should be calculated as in the deterministic case, and the term, this term, the third term, the first term of the second integral, second integration, will go to 0 if a goes to infinity, exactly because as in the deterministic case. But if we use stochastic analysis, then this convergence will be in the mean square sense, where integration will be also with respect to the random variable and the expectation, given expectation. So the last two integrals on the right-hand side, they will be simplified as well if we use the assumptions on the mortality rate and g. So this is independent of s, so that we get this term here from the first term on the right-hand side, and the last term will be replaced by this one. So we get an integral equation with respect to the size a of t, and then we have to calculate the only term left. So this term should be calculated as in the deterministic case. And this is done again by integrating the stochastic MFE along the characteristics, and we get a similar formula as in the deterministic case, but the difference is this stochastic exponential. So instead of the usual exponential, we get a stochastic exponential, which can be calculated using this direct formula. So this stochastic exponential satisfies the standard equation for exponentials, but the result will be different. We have this additional term in the stochastic exponential, and this is because the chain rule in stochastic analysis is different from the chain rule in the usual analysis. So this is chain rule, stochastic chain rule, or Ito's formula, where we, in addition to the first derivative of the function f, also have the second derivative, so the second term in Taylor's series. So this explains why we get an additional term in the stochastic exponential. And now we can summarize our calculations, and we obtain a stochastic delay differential equations with respect to the size of the adult population A of t. So this is an additive term, which we also observed previously. This part is deterministic, is equal to the deterministic part of Nicholson's model. And then we have this additional stochastic term, which we now have calculated explicitly. So this term contains the mortality rate of the juveniles and these two stochastic exponentials. So this is a stochastic process, which again, in the deterministic case, is simply constant, so that we can rescale it and interpret this coefficient as the production rate. But still, in the stochastic case, we have a stochastic process which cannot be interpreted as rescaling of the production. So this is the result, which is which generalizes a little bit the Nicholson model. To get this, we again use the same birth rate function, beta, as the exponential decayed function with two constants, p0 and theta, and assume again that the mortality rates are positive constants, so that we get this expression for the function b in this equation, this function. And this results in the following stochastic version of Nicholson's ball of lice model, where we have this additive term, and in addition, this multiplicative term instead of the constant p. So this is the explicit formula for this stochastic term, multiplicative stochastic term, in the stochastic version of Nicholson's blow of lice model. So let us now compare these two models. So this equation is obtained using an additive noise and the assumption that the mortality rate is independent of the this production part. And this what we have obtained from the first principles, from the conservation law. So this part contains, this version contains an additional multiplicative noise, which again is due to the mortality rate mj in the coefficient p, which is constant in the deterministic case, but which is a stochastic process in the stochastic case. So this is an equation which is very different from the equation, stochastic Nicholson's equation, which is usually observed in the literature, studied in the literature. We can also incorporate more general stochastic noises into the model. The Brownian motion is just a standard example, which is continuous example of a continuous stochastic process, but there are also discontinuous stochastic processes like the Poisson process, and so on. so that we can replace B by a more general stochastic process, which is known as a semi-martingale. So this process admits a stochastic integration. So you can integrate with respect to the Brownian motion, even if B is nowhere differentiable and has unbounded variation. And we can also integrate with respect to more general stochastic processes. And the most general stochastic process, kind of stochastic processes we can integrate over is the semi-martingale. So we can incorporate more general stochastic noise into the model under some additional assumptions on the jumps of this process, which I will explain a little bit later. In this case, the stochastic version of Nicholson's equation is very similar to what we get in the case of the Brownian motion. So we still have an additive noise of the same kind and the same deterministic part, and also a similar multiplicative noise, alpha, but the formula for the stochastic exponential will be very different in the case of an arbitrary semi-martingale. So this stochastic exponential still has to satisfy the standard equation for exponentials, but the resulting formula, the formula for x, is very different. It's the Dolian formula for the stochastic exponential satisfying this equation. So now we can explain why we have to assume additional conditions on the jumps of the process. This is because we want this factor be positive. So if this factor should be positive, then the jumps of the stochastic process should be bigger than -1, and this is equivalent to this assumption which I formulated earlier, the assumption on the jumps of the integrating process Z semi-martingale Z. And in addition, we have this quadratic variation, which is defined in the standard way. For the differentiable process, it's simply 0. For the Brownian motion, it is equal to t. And if we have an integral of g with respect to the Brownian motion, then we get the integral of the squared g, square diffusion, dt. So this can be calculated in a general case, in the case of the Brownian motion, and in the case of the an arbitrary semi-martingale. So these are the references I used in my talk. The results were published last year in Physica A. So it's, as I said, a joint work with Lev Idels and Ramazan Kadiev. And in the first part of my talk, in the deterministic part of my talk, where I produced Nicholson's blowflies model from the first principles, is based on this review paper, where we also have a literature review for this period. So I use notations and the ideas from this paper. Now I still have a couple of minutes left, so I just want to look at a more general model, which is known as the recruitment delayed model, which contains two parts usually. This is the production part, which is contains delay, tau, the maturation period, and the degradation part, or containing mortality rate, and which depends on A at time t. And A is the size of the adult population. So that a usual way to append a stochastic term is an additive term. So we use again this part and interpret this as the uncertainty in the mortality rate, but implicitly this term also contains the mortality rate of the juveniles, which means that we actually end up with an additional multiplicative noise if we perform the same calculations using the stochastic MFE. Then we get this more general version of the of Nicholson's blowflies model. Again, alpha, the multiplicative noise, can be calculated explicitly in the case of the Brownian motion, and the Brownian motion again can be replaced by an arbitrary semi-martingale Z, so that the equation remains unchanged formally, but the stochastic noise, especially the exponential, stochastic exponential, will be different in this case. So this was all I wanted to report about. Thank you for your attention.